So first of all, I would like to thank the organizer for giving me the opportunity to present our results about collective Rydberg excitation of atomic gas confined in a ring lattice. And this half an hour before your lunch, I have divided in 4 different points. The first part is I'm going to describe my system, our system, and then the second and the third part are related to the results, and I have divided in 2 different regimes. In the first regimes, we assume that the interatomic excitation is much stronger than the laser interaction, and the second part, the regime, is of a strong laser driving, and I will show you there that we can create entanglement particle states, and I will finish with some concluding remarks. So let's start with our system. This is my experimental setup. This is what we want to do. We wanted to study a ring, Rydberg atoms confined in a lattice, and then we took the nicest and a more structured and symmetric scenario we could find out, which we have a ring lattice, which is plotted here also, where we have L sides, we have a periodicity on the micro range, and then we have a large spaces, and then we have a gas of bosonic atoms. For the moment, I'm going to assume that they have the same amount of them per each side, and they are confined in this lattice. So I have N0 ground state atom bosonic in each of these minimum of the lattice. And then no atomic, so there's no particle exchange between the sides. I assume my atomic motion is frozen. And in addition, I'm going to assume that the Barnier, this sigma here represents the size, the size of the atomic wave function. So they are much smaller than the separation between 2 minimum of the potential. And I am assuming that all of the atoms are occupying the ground state of my lattice. So I am going to model them with 2 states, the ground state and the Rydberg states. And then I have a laser which I switch on instantaneously, and is characterized by a Rabi frequency and a detuning. And that's going to drive the transition from the ground to the Rydberg state. So this is how my Hamiltonian look like. I have used a spin model. They have here the interaction with the laser. I have this is already the collective Rabi frequency, which is proportional to the square root of the number of atoms I have per node. And then I have here the detuning, and I have here the Rydberg interaction. So I'm assuming only nearest neighbor interaction. I am considering only van der Waals interaction. I have at most a single Rydberg atom per side. And I consider only next neighbors interaction because the next nearest neighbor interaction is this factor smaller, that it goes to 64 when the number of sides in the lattice increase significantly. So what we are going to do is to study the dynamics of this system. I'm going to assume that I start with a system where no Rydberg atoms are excited, all my atoms are in the ground state, and I'm going to study the dynamic standing for this ground state. So if I do like that one, the dimension of my Hilbert space is 2 to the power of L. However, I have this nice symmetry, as I told you. I have a ring lattice with 2 symmetries. First of one is cyclic shift, and the second one is the reversal of the order of the size. The cyclic shift is what is represented in this nice scheme, so you cannot see nicely. MT is ground state atom, Rydberg is the red color, and then it doesn't matter, here in that one I have 1, 2, 3, 4, and so on. And here I have in a different notation, and it doesn't matter, both systems are equivalent. So my Hamiltonian is invariant under these 2 operations, this cyclic shift and the reversal of the order. And in addition, my initial state, which I'm going to note with 0, is the vacuum state, satisfies that these are eigenstates of both operators with eigenvalue 1. So this is what we call a fully symmetric state. And from my complete Hilbert space, only a small amount of my states satisfy these 2 properties. We are what we call this fully symmetric state. Our Hamiltonian conserves the symmetry. Our initial state has this symmetry. So that means that our dynamics is going to take place only in this fully symmetric state. And that gives rise to a significant reduction of the states we have to consider. So it goes, for example, for L equal 10, we go from 10,020, so like 1,024 to 78 states. So now, I'm going to solve, as I told you, this time-dependent Schrodinger equation of this system. So I went the other direction, sorry. So now let's start with the first part of the result. In this regime, we have a strong interatomic interaction. This is, first of all, I assume that my laser is on resonance, and then this is my Hamiltonian. I only have the part of the interaction with the laser and the part with the interaction with interatomic interaction, the Rydberg-Rydberg interaction. So in this system, there are two different energy scales, and at the same time, two time scales. The first one is associated with the laser interaction, which is given by this energy proportional to the Rabi frequency, and then tau naught is what is the time scale. And the second is the Rydberg-Rydberg interatomic interaction, which I know by beta. And this is the time scale of the Rydberg-Rydberg interaction. So if I look in this Hamiltonian, if I look to the interaction part of the Hamiltonian, what I have is that the eigenstates are divided in L subspace. I have L rings, I have L subspace. They are degenerate, and they are characterized by the pair of neighboring Rydberg-Rydberg interactions. So that means nu equal to 0, there are no pairs of Rydberg-Rydberg interaction. Nu equal to 1, I have at least one pair. Nu equal to 2, I have two pairs. So this is what is represent this Hamiltonian, this kind of scheme here. These are the states having new pair of neighboring excitation. So what is H node doing? My laser, which is driving the dynamics within this set of the generated states, and then it's also making the coupling between neighboring and, so like having one more neighboring excitation and pair of neighboring excitation and two more. This is what the H node is doing. So what I want to discuss now is this regime where beta, my Rydberg-Rydberg interaction, is much larger than the interaction with the laser. So that means that if I am in this subspace where I only have mu neighboring pair of interaction, it's a very small probability that I get coupling to the states in with one more pair of neighboring interaction. So my assumption, what we are doing is to work only in one of these subspace where I have fixed the number of pairs of neighboring interaction. As I told you, I am starting with this state where there are no Rydberg excitations, so this state is the vacuum for Rydberg, so we have nu equal to 0, and this state, we keep in this subspace. We are not going to consider the coupling to higher subspace. That implies that they have a further reduction of the Hilbert space. So we went from almost more than 1,000 to 78, and now we have only 14 states for L equal to 10. And this is what we call this is the perfect blockade approach, which is valid only for T much smaller than the time scale of my interaction. So how does the dynamics look like? In this nice scheme, what I have, which direction am I going? It's not doing nothing. This is not doing nothing, that's perfect. No. Now you have seen all the talk. Here. So in this nice scheme, what I have is zero excitation, that the states I have for the example of L equal 10 sites, and then I have zero excitation 1, 2, 3, 4, and 5. And we start in this state, and then what we see, there are several paths connecting all the states we have, and all of them have different possibilities. So the maximum number of Rydberg states I have is like L divided by 2, the integer part of this L divided by 2. And the important part here, this is why I saw this scheme, is as you can see, there are several paths that they don't end up in this 5, in this 5 excitation states, and the EMAP in this 4b and 4c that they are not connected to the 5, which is these are the frustrated states, and as they become important in the dynamics, what I will see is that my dynamics, the dynamics of this system, is significant, and it's divided clearly in two different regimes. For short times, we have a universal behavior, is independent of the size of my lattice, while for longer times, there appear a dependence on the size of the lattice. And of course, you can imagine the amount and the kind of frustrated state strongly depend on the size of my lattice. So let's have a look on the dynamics. So one of the first things we look is the Rydberg density, which if we multiply by the size of our lattice, we get the number of Rydberg excitation. This is plotted here as a function of time for different lattice size, 10, 15, until 25. And this is a blow up for the short time for L equal 25 and 10. So this picture is what I have told you about this universal behavior. We have that we cannot distinguish the dynamics for these 10 and 25 cases, and we have in both cases an increase proportional to t to the square, and actually the maximum is the same for both of us. However, if we look in this picture, we see that in the long time regime, all of them have oscillation, and the oscillation look very much different. So what we saw is that for longer time, this density of Rydberg oscillates with a similar frequency for all the cases and about a mean value. And then what we see here is the different, like we have the amplitude, it's completely different for each cases. So that was regarding the Rydberg density. So we wanted to understand if our system had any kind of correlation. We defined the density-density correlation function as follows. And then k is the distance between the sites we are looking for. So it's n number of Rydberg in n1, and then number of Rydberg in n1 plus k. And this function is plotted here as a function. You have here time, and then you have distance. We are in this perfect blockade regime, so I am not allowed to have any excitation in k equal to 1. This is what we are seeing here, perfect blockade. There is no density-density correlation function. And if we look at short time, we have the same correlation for all of them. That means we have our first Rydberg, and then it's all other sites in the ring have the same probability. As time goes, we have a nice pattern having correlation, not having correlation, having and not having correlation. However, as time increases, this pattern is completely lost, and this is what is shown here. There is a line here that you cannot see. This is the time average of this function once we have passed this short time regime. And what we can see is that we have a peak here for k equal 2, and then everything is oscillating around 1, so we don't have correlation. So for long time regime, we only have short range correlation at k equal to 2. We also, and again too quick. So we also have a look in the two-party correlation measure, which is defined like that one. It takes into account the classical correlation and also the quantum coherence. And if both operators commute, it's reduced to the Kolmogorov distance. So in the figure on the top, I have this two-party correlation measure as a function of time. And then you again see this nice, I mean, there are different lattice size. Each color represents a lattice size. You have, again, see this universal behavior, and then as time goes and this frustrated state become more and more important in the dynamics, we get these differences. And in the figure on the bottom, we have the comparison between both for L equal 25. And what is important to see is that the quantum case, the two-party correlation measure, has a double head maximum here at the beginning that the classical version, the Kolmogorov distance, is not able to reproduce. So at the beginning, we have some quantum effect, and as time passes, the quantum effect really vanishes, and then we really see that the Kolmogorov distance reproduces very nicely the two-party correlation measure. And in the figure of the bottom, I have the entanglement of formation. It gives an estimation of the amount of resources needed, the quantum resources needed to prepare the state. And again, we see this kind of general of universal behavior, and then the oscillation. And you also see which as entanglement is important here. As time goes, it's really the amplitude of the oscillation decreases. So everything till now was done in this perfect blockade approach. And we wanted to estimate if we were right. What happens if we are not completely in the perfect blockade approach, and we allow the coupling between states that they don't have pair of neighboring Rydberg, and they have pair of neighbor Rydberg. So we could write, I mean, there are many equations here. I only pick up the two important one, or the two I consider they were important. We could write our Hamiltonian in such a way where P is the projection of the states of the only without pair interaction, and Q is the projector in the red of the state. So we keep the same approximation, and then we assume that the coupling, so like not the coupling, like the chains on these states that they have more than one pair of one or more pair of neighboring interaction is very small. So making some algebra, we are able to arrive to this effective Hamiltonian, giving us this time-dependent Schrödinger equation. And here I have the Hamiltonian for the part where the states are having no pair of neighboring excitation, and then is the coupling between those having no and one pair of Rydberg excitation. This is the same here, and here is the coupling between those without pair and with two pairs of Rydberg. So we have solved this Hamiltonian. Before showing you the result, I want to I have plotted here this is an histogram. For this example is all the eigenvalue, my full Hamiltonian, all the eigenvalue of the Hamiltonian with 0 detuning, and then I have 15 sites. And I have considered that my Rydberg interaction is 20 times the laser interaction. So what we see here is what I told you, that we have these sub-levels quite clear, but now due to the presence of the, I mean, they are not any longer degenerate due to the presence of the interaction. And what I am showing here is that this approximation, this is why I saw this figure, this approximation will be valid only in the case that the states in one subspace do not overlap the states in the next subspace. So for the case of 15 sites, 20, which is the example here, is the maximum we were allowed to have, the ratio between both interactions. If I increase the lattice sites, I should increase the ratio in order to have this approximation valid. And then we have, I have this nice figure where I plot here the density, the Rydberg density, and here is the correlation, the G2 function. In red, in this figure, is the perfect blockade, and then we have this B, the ratio. The other two cases are not computed in the perfect blockade case. They are computed for B equal 20, the ratio between both 25 and 35. The example is for L equal 20, and here is similar, different colors. What is important here is to see that the perfect blockade is a very good approximation for all this part of the time. It's almost, there's no difference, and there are only minor difference for above 20, this 24, and here 15, where there, I mean, we can also say that the agreement is very good, so there are not large interpretations. So once we finished this work, we thought, okay, let's see what's happening if we just, the first idea was we just wanted to analyze the spectrum of the system. And analyzing the spectrum of the system, we end up in this strong regime, a strong laser driving regime, which I'm going to describe you now. So going back to my Hamiltonian, I have the three terms again. So in one of these minimum of my lattice, what I have is two possible states, those two superatom states. The first one, P, is the one where all my Rydberg states are in the ground state. And the second one, R, we notate with capital R, is with one of them is excited. I keep again in the same regime where I allow only at most one Rydberg atom. And that was what are the states in this case. So I will use later on then. This is why I'm introducing you. R and G, this small one, they represent single atom Rydberg and ground state. So now, if I make omega very large, if I go to the very large regime, that means that omega is much larger than beta now, and omega is much larger than the detuning. So if I look to my Hamiltonian, this is the term it's going to dominate. So now it's, I'm sorry I could not avoid to put some equation on the way. So what we do is to try to diagonalize H naught in order to understand what is the physics of our problem. So first of all, we have this unitary transformation, which allow us to write the Hamiltonian in such a way. And in this part, I mean, you have three parts, x, y, h1, and h2. These are the parts coming from H naught, and this part is the xy spin chain model in a transverse magnetic field. You could recognize it. So now, if I have now the Hamiltonian written in such a way, how does it look the Hamiltonian? How does it look the eigenvalue for this system? How is my spectrum look like? So now, in this Hamiltonian, which is dominating the dynamics, it's going to give me again subset of states which are degenerate, and they have this eigenvalue. When I have the presence of the other two parts, they are not any longer degenerate. So this subspace are states with nearly degenerate with eigenvalue of this operator, which is the Pauli matrices, the sigma zeta, and Hxy is driving the dynamics within this subspace. H1 and H2, what it does, they does coupling the subspace, the neighboring subspace, and also those that they differ in m equal to 2. So the transition rates between different subspace is proportional to delta squared divided by omega and beta squared divided by omega. So if I have a large omega, I could neglect this H1 and H2. And this is what we did. Yes, now here we are. So we are going to analyze only this part of the Hamiltonian, and now the eigenstates of this Hamiltonian, of this part of this operator, are plus and minus, and they are just a combination of these superatom states with Rydberg and no Rydberg, and of course I have to use the unitary transformation. So to solve this Hamiltonian, we make a second step. We need to make a second step, and then we introduce the creation and annihilation operator of a spinless fermion, Ck and C dagger K, and this is we use it through the Jordan bigness transformation, and then we get this nice Hamiltonian where this last term we have it due to that we have a ring, due to the symmetry we are having. And then we have different operators. M plus counts the number of fermions or superatoms in these states. We have this operator, the eta dagger, which creates an excitation of H, X, and Y. And then we have to distinguish between a L with a odd, L odd or L even, and this is what is alpha. So here is, after diagonalizing, this is what I get, with again giving the expression on alpha. How does this state look like? The ground state look like that one, and then I can use eta dagger to create excited states with 2 fermions, with 3 fermions, and so on. And what is important is that all these states, and there are much more here, I only put the first 3, they are eigenstates of my initial Hamiltonian, of my complete system, if I am in this strong laser driving. So our question was, okay, now we want to switch on the laser slowly, and we want to see if we are able to populate one of these states. So which are our initial condition? Our initial condition is the same as before. I start with an initial state that there is no Rydberg excitation there. It's just this 0 state, which are now in terms of superatoms. I can write like P. And for t equals 0, I have 0 Rabi frequency, but I have a certain detuning. Again, this Hamiltonian had the same symmetry properties that before, and my state, it's a fully symmetric state. So the symmetries of my system are giving me the selection rule of this transition. And I wrote you here again the symmetry property of the system, and that means that what it's telling me is, as before, I can only assess fully symmetric states with this system. which are the fully symmetric states of the list I put you before. The ground state is fully symmetric, and then I have from the all possible one fermionic states, there are L possible one fermionic states, there is only one. This can be considered like a spin wave or superatom extended over the complete lattice. And then we have two fermionic states, they are entangled, which are given here. So now, these are the states I'm going to be, I'm able to access them, but how I am able to access them. So here is the spectrum of the Hamiltonian. This is energy as a function of omega, and there are two different cases. The one here is negative detuning at the beginning, and this two is positive detuning. So when I have negative detuning, it turned out that my initial field Rydberg states, this 0, it's not the ground state of our system. So what we have is that as we increase omega, this state is encountering several avoided crossings. So in order we want to achieve one of these fermionic states I told you, we need something like optimal control theory to tell us how to cross either adiabatically or diabatically all these crossings. In the other case, that's not the case. When we have positive detuning, our initial state is adiabatically connected with the ground state. So now we are adiabatically connected to the ground state, and the question comes, how can we go from the ground state to these lines that actually you cannot see? There's one is here when the blue line finishes, and there's several two here. So how we can go from the ground state to the other? So we thought several possibilities. The first one is just have a sequence of pi pulses with appropriate frequency. So we will have a first pi pulse to go from ground state to the first excited state, to the spin wave states, and then another one with a different frequency to go to 2 fermion. Another possibility is to have the tuning which oscillates, and then that will, when we have the correct frequency, which is that one in resonance with the first state, we will have Rabi floats between our ground state and our excited state. Of course, we have to take into account that from 1 to 2, we also have omega. But then using the tuning, like large this part, the constant part, we will avoid to be in resonance. So that was what we were able to solve. I mean, not to solve. We wanted to propose a mechanism to go from this from the field Rydberg case to populate this one fermionic state, which is a spin wave, or these two entangled states. So now when this finished, we thought, okay, can we assure that we have the same amount of Rydberg atoms per site or not? I mean, we know that there have been already experimental experiments where they don't have they introduce disorder on the lattice using this speckle potential or standing wave with uncommensurate frequencies. What we did was, okay, having disorder means that we have a spatial variation of our Rabi frequency. That is a small variable, a random variable around this minimum, about this medium value, and then that was experimentally done already. So we thought to propose something different. We start with a superfluid stage, which is given here. B is the creation operator in a ground state atom. And what we thought is, we are not experimentalists, so we thought that could be done is to raise up suddenly, very quickly, the lattice in such a way that now the number of atoms I have per site is not any longer constant. So my having a spatial variation of the Rabi frequency comes through having not the same amount of ground state atoms per site. So if we were able to do that one, what we have is an Anderson Hamiltonian. I'm not going to describe you how we solve now the case. And what we look is the same. Before, when you are in the ground state, you only are allowed to go to one of the states with one fermion. Now this is not any longer true because we have lost the symmetries completely of our system. So from the ground state, we can go to many of the excited states with one fermion. And this is what we have plotted here, the absorption profile of this transition as a function of omega, with for two different cases of number of Rydberg of ground state atom per site. And then we see that in the case with no disorder, we will have a peak And when we have disorder, we have these nice figures showing that there are many states that they are allowed. And what we saw here is that we can introduce disorders without in an optical system without having any motion of the atoms. The atomic motion is always frozen. So to conclude, I have shown you today in the first part the strong interatomic interaction, that the temporal evolution can be divided essentially in two parts, short time and universal, long time depend on the lattice size. And for example, regarding the correlation, at short time they're important for long time, for long distance, but when time goes, they're important only a short range. And in the second part, in the strong laser driving, I can show you that we can create and explore these collective many particle states, that they are entangled and extend over the entire lattice, and we could study fermions in a disordered potential without external motion taking place. Before I want to show you which are, the work has been done with Beatriz Olmos, which is the PhD student, and Igor was said several times, but no picture was shown. So this is Igor Lesanowski, which is now in University of Nottingham. And when I was this summer in the COCOMO meeting, there was this ultra-cold molecular meeting in Boulder. We went to visit the Rocky Mountain National Park, and I found this nice picture there in one of the stops you can do. I was Rydberg here, so I thought it's much good to show here. It was a different kind of Rydberg. So Robin Cotte showed you the original Rydberg. I saw here you a different Rydberg. It's also the name it was given to the Rydberg, but it's not the same Rydberg person. And that's it. Thank you for your attention.
The last questions is,
it's probably a very naive question, but also obvious. How much of what you showed us in the first part of your talk would carry over into a linear lattice without the cyclic boundary conditions? Do you have any idea?
We wanted to do the linear lattice, but we have not done it. Indeed, I mean, when we increased the size of the lattice, there were, I think we did calculation for 25 times even longer. Many of these things keep. So if you look locally, it could be that that's part keep it. But we were thinking, we are now considering different kind of site of lattice.
yeah, that would be also my question. I mean, would it not make sense to make kind of a cluster expansion where you have like next neighbor and then you take into account like groups of 4 sites which eventually could interact, instead of having this cyclic symmetry, which is really extremely special and probably.
I mean, the cyclic symmetry was really nice because it really makes us simple to treat the system.
I think it's totally unrealistic.
Yeah. Well, there were 2 experimental proposals about the lattice of a ring lattice. So I might have the reference there, but I don't think they were never work out. I was happy when Oliver said that they were thinking about to do all the kind of symmetries. And one of the things we want to analyze right now is the 2D cases, like the lattice they are working normally, including other kind of interaction.
So I have a question about this blockade condition of the first part of the talk. It's kind of, it looks like it's not consistent, right? So on the one hand, you assume that the interaction.
What do you think? Why do you think it's not consistent?
I mean, since we are neglecting next nearest neighbor interactions, right?
For example, in our lattice, we only have to have one Rydberg, no Rydberg, one Rydberg, no Rydberg.
But that's because you have the factor of 64, right? So you neglect the next nearest neighbor.
Yeah.
Because you have the 64 factor, but at the same time, you assume that the nearest neighbor interaction is much larger than the omega.
Yeah.
So now the next nearest should also be at least on the same order than the omega, right? So it will matter, even though it's smaller than the, if you fully blockade in the next nearest.
Do you think if I am fully blockade, I should consider the next neighbor?
At least, yeah.
In order to have. But what you saw is that when we consider in this adiabatic approximation, we don't have really large difference. Like the results I showed you here, that was a way of including the interaction until b divided b to the power of 2 minus 2, there's no difference. Okay. So these are computed perfect blockade results, and these are not perfect blockade results. This is doing with this beyond the perfect blockade, and there's not much difference between.
So it's a tiny window of interaction, so that this works. So.
As a chemist, when I see a ring, I think of benzene or something like that.
That's nice.
And actually, you know, some of the things you were talking about here are not dissimilar from the way that people have treated chemical bonding in ring compounds. For example, by taking only the nearest neighbor interactions. And I wonder if you've thought about those kind of analogies and whether there are techniques you can
no, actually, one of the techniques we are using to produce in an efficient way the basis we need to work out is from crystallography. I have a friend who is a crystallographer, and then we just use something called bracelets and necklace. So it's really just, it's an algorithm, very short, which is the efficient way of producing this kind of states we have. Because at the end, when crystallography, what this state can, it's 0, 1, 0, 1. So 0 when you don't have Rydberg, 1 when you have Rydberg. So we profit from crystallography, the way they treat the crystal. And that was just praised. I mean, it's well known in the community. I never hear about that one.
Okay, I don't see any more questions. Then let's thank all the speakers. Before